Okay, so hello and welcome back. So the next problem that we have here is question number 18, and the question is, let f be a function from R to R. So we have a function f from R to R that be the signum function which is defined as f of x is equal to basically 1, 0 and negative 1 for x is greater than 0, for x is equal to 0, for x is less than 0. So and g of x, and g is also a function from R to R, defined as g of x is equal to the greatest integer function where basically we use this notation for the greatest integer function, where this notation is the greatest integer less than or equal to x, or equal to x. Now the question that we want to answer here is basically do FOG and GOF coincide in the interval 0, 1. Okay, so to solve this problem, basically what you can do is that of course you know that FOG and GOF are for example, when you say FOG of x is equal to f of g of x, and GOF is equal to GOF of x is equal to g of f of x, right? Now if it's this function and g is this function, and if I want to calculate FOG, so I need to basically to calculate FOG, we need the output values of basically g of x over some period, and the reason for that is that because FOG is equal to FOG of x, let's say, is equal to f of g of x. Now of course if we have no constraints on x, then it's not easy to basically talk about this. So I'm going to say that let, for example, x belong to some interval, for example 0, 1. 0, 1, right? And if that is the case, then basically g of x is equal to, g of x is some function which is the greatest integer function, and the domain is x, the codomain, I'm sorry, the domain is r, the codomain is r, right? So that what that means is that g of, for example, if you go for g of 0 is the greatest, or is the basically that would be the greatest integer less than or equal to 0. What is the greatest integer less than or equal to 0? It's equal to 0. And for example, if you go to g, if you calculate g of 0.5, that's still equal to 0. If you go to g, if you calculate g of 0.8, that's still equal to 0. And if you calculate g of 1, that's equal to basically 1, right? So what we are going to, so what I'm going to do is that I'm going to say that x belongs to not this interval, but this interval of 0, 1, not including 1. I'm going to say that x belongs to 0, 1, not including 1, only the values between 0 and 1 in the real numbers, and x belongs to the real numbers. So what that means is that then this is not a problem anymore, meaning that all the values between 0 and 1 are going to give me an output of 0, which basically all of this means that g of x is equal to 0 if x is some value between 0 and 1, right? If x is some value between 0 and 1, then g of x is going to give me 0, which means that FOG of x, which is equal to f of g of x, is going to be equal to basically f of 0, and f of 0 is equal to 0. F of 0 is equal to 0, right? And this is assuming that x belongs to the interval 0, 1, right? Of course, the question that is being asked here is do FOG and GOF coincide in this interval that includes 1, but for now we are not going to bother about 1, because that would make things unnecessarily complicated. So for now, I know that basically FOG is equal to 0 for all x's belonging to this interval, which include all the x's 0, all the x's lying between 0 and 1, right? Now, if I want to calculate GOF of x, that is the same thing as g of f of x. Now, f of x is equal to, as you can see over here, f of x for all the x's between, for all the x's that are equal to 0, f of x is equal to 0. And then for all the x's greater than 0, then f of x is equal to 1. Which means that for all the x's between 0 and 1, so here we have all the x's greater than 0, and here we have all the x's equal to 0. So that means that for all the x's greater than 0, f of x is equal to 1, right? So f of x is equal to 1 for x's greater than 0, or between 0 and 1, you can say. So which means that if x is greater than, if x is between 0 and 1, then of course f of x is equal to 1. which means that I can say that GOF of x is equal to GOF of x is equal to G of f of x, which I can write as f of x is equal to 1, so G of 1. Now this is assuming that x is between 0 and 1, of course. Now G of 1, what is G of 1 here? This is the greatest integer function, meaning that the greatest integer less than or equal to 1, which is equal to 1, right? So what that means is that assuming that x is some value between 0 and 1, then FOG of x is equal to 0. FOG of x is equal to 0, and GOF of x is equal to 1. Now we don't really, and the question that was being asked here was that whether FOG and GOF coincide in this interval. So in this, the only difference between this interval and the interval that we have here is that basically the interval over here is basically this includes 1 as well, but this does not include 1 here. Now for all the values between 0 and 1, these two functions do not have the same outputs. This function has, FOG has the output 0, GOF has the output 1, and so since basically between 0 and 1 the outputs are not the same, we don't really have to care about x is equal to 1. And therefore I can say that FOG and GOF do not coincide in 0, 1, and that is the answer to this question. Now the next question that we have is rather an interesting question, and that is that we want to calculate the number of binary operations on set A, B, the number of binary operations on set A, B are choice A is basically 10, choice B is 16, choice C is 20, and choice D is basically 8. Now, to answer this question, you need to know basically the definition of the binary operations on a set. We said that basically a binary operation star. We said that the binary operation star on a set A is a function star basically the Cartesian product of A and A to A, meaning that star is a function, the domain of this function becomes the Cartesian product of A and A, and the codomain of the function is the set A. Meaning that, for example, if you have the set, if I say that basically A is equal to the set containing A, B, then the Cartesian product of A and A would be would be basically a set over here which contains A and B, and the set over here A and B, and then we have the Cartesian product basically means this, meaning that the Cartesian product of A and A would be a set containing A comma A, all of these ordered pairs as A comma A comma B, B comma A, B comma A, and B comma B, right? And of course, we know that the binary operation star is a function from this set to A, meaning that the binary operation star is a function from this set, which is A, the Cartesian product of A to A. A is basically a set which is A comma B, and we have this set over here, which means that basically you can basically, I mean, theoretically what you can do is that you can take any possible basically subsets of the set subsets of this set, which is the Cartesian product of A and A. So what that means is that all the possible subsets of the Cartesian product of A and A, the number of them would be 2 raised to the power 4, because you have 4 elements here, and of course all the possible subsets of this set would be 2 raised to the power 4, and 4 is the number of elements that this set has. So that, which means that basically you can say that, for example, let's say that R1 based on this set is going to be equal to the set containing, for example, A comma A. R2 is going to be, for example, I don't know, A comma B. And R3 is going to be, for example, B comma A. And R4 is going to be equal to, for example, this set containing B comma B, and so on and so forth, until you have all the different 2 raised to the power 4 is equal to 16, until you have all the different 16 subsets of this set, right? And once you have all of the subsets, you can define star in such a way that basically that you have, for example, R1 to, for example, A, and you have to basically define star in such a way that R1 to A is a function, and then theoretically you can have the number of all of the different binary operations on the set A comma B. A comma B would be basically the possible number of the subsets of R1, because then you would get, for example, R1 to A, R2 to A, R3 to A, R4 to A, and so on and so forth, which would be 16. So which means that the number of binary operations on set A would be simply 16, which is this choice over here, the choice B basically. Which brings us to the end of this chapter. Okay. Now there is a note over here. That says that, as a historical note, which must be interesting, The concept of function has evolved over a long period of time, starting from R. Descartes, I think a French mathematician, 1596 to 1650, who used the word function in his manuscript Geometrie in 1637 to mean some positive integral power x raised to the power n of a variable x, while studying geometrical curves like hyperbola, parabola, and ellipse. James Gregory, 1636 to 1675, in his work Vira Circuli et Hyperbolae Quadratura, I don't know what language that is, 1667, considered function as a quantity obtained from other quantities by successive use of algebraic operations or by any other operation. Later, G.W. Leibniz, 1646 to 1716, in his manuscript this doesn't look like German, but I know that Leibniz was German, written in 1673, used the word function to mean a quantity varying from point to point on a curve, such as the coordinates of the point on the curve, the slope of the curve, the tangent, and the normal to the curve at the point. However, in his manuscript Historia 1714, Leibniz used the word function to mean quantities that depend on a variable. He was the first to use the phrase function of x. John Bernoulli, 1667 to 1748, used the notation phi of x for the first time in 1718 to indicate a function of x. But the general adoption of symbols like f, phi, psi, and so on and so forth to represent functions was made by Leonhard Euler, 1707 to 1783. In 1737, in the first part of his manuscript Analysis Infinitorium. Later on, Joseph Louis Lagrange, 1736-1813, published his manuscripts Theorie des Functions Analyticus or something like that, in 1793, where he discussed about analytic function and used the notion f of x or phi of x, etc. for different functions of x. Subsequently, I don't know this mathematician, 1805 to 1859, gave the definition of function which was being used till the set theoretic definition of function presently used was given after set theory was developed by Georg Cantor, 1845 to 1918. The set theoretic definition of function known to us presently is simply an abstraction of the definition given by this mathematician, I cannot pronounce the word, in a rigorous manner. So that brings us to the end of this chapter. So the next chapter that we have here is chapter 2 of these of basically of the book, which is inverse trigonometric functions. So in the next course we will talk a little bit about inverse trigonometric functions, and so I'll see you in the next video. Thank you.